you see he has to start building up charge, and that's a string of LED lights that are lighting based on his hitting this little sheet. And so I said, walk around campus, start charging. He left the lab, walked around campus 1.2 miles, put that little sheet in there, and he started charging up this little capacitor. So you could think about, when I'm walking, I'm charging my cell phone. Wouldn't that be nice? You don't walk, you run out of cell phone battery. We were talking about laser-induced graphene. Remember, we said a laser that's found in any machine shop can write one of these patterns. It's really turned out to be an amazing, amazing tool. So here's the laser system. We talked about this, and this is what it looks like, where you get a film, then you get this graphene growing on the film. And here's what it looks like when you look at it with aberration-corrected TEM, is that you can see that all of this moire pattern, it's different levels there, and you can even see 7-membered rings. If you have a 7, you're going to have 2 5s next to it. So generally graphene is all 6s. So if one ring expands and is 7, then the 2 rings are going to have to contract. And so it'll go and be on the sides. You'll have 2 5-membered rings. And so what would happen is you'll see that, and you can see the 5-membered rings and the 7-membered rings. And we looked at what's the power that's needed to get these things to start forming. And this has just been a gold mine as far as publications. Like I said, about over 500 papers a year are being published using this method. It turns out now it's probably the biggest method around for making graphene, the most used method, because you can do it in air. As the laser goes across, the temperature can reach 2,500 centigrade. Well, why doesn't the carbon just burn up? And it's because as you're lasing, there's outgassing. So the gas is coming out, so it's preventing oxygen from getting in and burning it up. So it's really convenient. You can even make this in the air. All other graphene you grow, and you have this very strict heating with complete exclusion of air, or else that graphene sheet would oxidize. And this is all being done in air. And I talked about all these different things that we've done. We've made LIG, we've modified it, we've done roll-to-roll, but now the world has far surpassed us in the sense of making all of this stuff. And I mentioned last time that my students took a picture of me and they put it in the computer, and then they gave me a piece of artwork. Here's an important question. Why would anyone believe that a man named Jesus died and rose from the dead? If you don't believe in the physical resurrection of Jesus Christ, send an email to tour@drjamestour.org and we'll set up a meeting, and I will tell you about why I embrace the resurrection of Jesus Christ. And so they took this picture of me and they just fed it in, and that's the picture I took. This is hanging in my office, and right here it says graphene here, but that's my picture in graphene. So if you wanted your picture in graphene, you could have it now. That means wherever it's black, it's conductive. And here's another picture in my office, and this was hung in a museum actually. So an artist gave us a pattern where in his mind, this is what he envisioned graphene looking like if you lived among the graphene layers. Now, it's not really quite exact because he's really crunched down some of these aromatic rings and made them far from a typical hexagon. But, you know, this is an artist's conception on this, and so he gave us this pattern, and we did this on a piece of paper, and a good piece of paper for him. But you have to make the paper so it's not flame retardant. So the paper would normally catch fire. So you dip it in boric acid, pull it out, and then it become flame retardant, or you can just buy some flame retardant spray at the fabric store and spray it on there, and that way it won't ignite. And this is in a display in my office as well, so if you wanted to come and see that, you're welcome to. And we actually published a paper called Graphene Art. We didn't put my picture in there, but we put some other pictures. And I put a picture of Lovett Hall. I gave it to the Office of Technology Transfer, and it's hanging in there. And so we know that the amount of energy that you have to do before you start seeing graphene. So as you increase the amount of energy, you can start getting this graphene. And so we got these patterns, and you get these letter R's. You can write these letter R's. And so if you change the parameters, instead of having that foam, you get these sort of fibrils that are coming up. And these fibrils can grow as high as 1 millimeter. So it's this graphene foam-like fibrils, 1 millimeter. This is great. This is great because it gives you a huge surface area to do sensing with. So if you just have a sheet of graphene, you just have that one layer. But if you have all of this, now you have all this porous layer, so porous material. So for many things, it's really nice. And you see here that you get the 2D band and the G band. The D band happens because this is, if you just take a sheet of graphene and you just start to bend it, you will see this D band, which is the disordered band or the diamonoid band, the sp3 band. So these carbons are all sp2, but if you start to bend them, they think they're sp3, and they start resonating there. So it's really interesting. If you just take a carbon atom that's sp2 and you just start to take the groups and start to bend them around, it'll start looking like an sp3 carbon atom. Really, really quite amazing when you do this. And so this is where we actually finished off last time, where if you do it in air and then you put a drop of water on this graphene layer, the drop of water completely splays out here. So it'll be completely splayed out. So you get a 0 degree contact angle. So it's super hydrophilic, meaning it just loves water and the water just totally splays out. If you do it under an inert atmosphere, so in other words, if you do this under an inert atmosphere, so you need a window here. It can't be glass. It has to be something that wouldn't absorb the 10.6 micron laser. So we use zinc selenide. Zinc selenide doesn't absorb in this region. So you have to find a glass that doesn't absorb in the region where the laser is being used. And normally zinc selenide, a piece of zinc selenide that's just like this, would be $1,000, but we got it for like $50 because we got it on eBay and it had a little chip in the corner. So for some people's applications, it couldn't work, but for our application, it was fine. And so we just put that on there. And so you're writing right through this little window. And then you can run it in an inert atmosphere. So if you're in an inert atmosphere, then there's no oxygen around, so you can't get oxygenated edges. And it becomes super hydrophilic. If you're over 150 degrees contact angle, this contact angle, that is called the contact. If you're over 150, it's called super hydrophobic. Super hydrophobic. So water just totally beads up, and it's very hard to keep the water on there. The water just runs. If you have any slight tilt, the water just shoots right off. It just rolls right off. It's like a ball bearing on a platform. And so you have to. So you have this. This device that really levels it out so the bead doesn't go away, and then it measures that angle relative to the surface. And so what we did is we took a sheet of polyimide and we drilled holes in it, and what we did is we made it super hydrophobic. One side super hydrophobic and the other side super hydrophilic. And so the water, you can put in an oil and water mixture, and only the water would go through and not the oil. So you see, you can get separation. I mean, this is really important, say, in the oil industry. So you take a sheet of polyimide and you have the laser drill holes in the polyimide, no problem. And then what you do is you make LIG, laser-induced graphene, on one side in the air, on the other side in an inert atmosphere. So it's got a super hydrophilic and a super hydrophobic side. So if it's super hydrophobic, the oil can wet the surface and it can move on through, but the water can't. If it's super hydrophilic, the water can wet the surface, but the oil can't. And so that moves through the other way. So you can get separation that way. And then this turned out to be really amazing. These super hydrophilic, the thing that water could contact very well, doesn't foul, meaning that you can put it in with organisms that will build up a biofilm normally on things. So if you take a piece of Teflon and you stick it in the ocean, I mean, within a day that is just covered with a film, a biological film. But if you use this because it's super hydrophilic, what happens is the water totally splays out on there. So you would say, well, can't these microorganisms, now that they're water-based, they should stick to it because you got that water. What happens, it's like if we take a doorknob and you put oil on the doorknob, you go to turn the doorknob, you can't grip it. So when there is a layer of water that is in full contact with that surface, the microbes can't get to the surface because it's got this layer protecting it of water. It's when the microbes can displace the water, then they can hook onto the surface. So you see that you can play this game, and so no microbes stick to it. So if you just look at polyimide, the live organisms stick to it, the dead organisms are sticking to it, and these polymeric materials that they emit, these biofilms that they emit, stick to it as well. If you just use graphite, live and polymeric materials stick to it. If you use the LIG, nothing's sticking to it. That's really good. That's a good thing. So you can now have a surface that microorganisms don't stick to. If you want them to stick to it, make the surface in an inert atmosphere, and then they'll stick to it. And so what you can do is you can take two surfaces, make a surface here, have a space, make another surface here, and you can apply a voltage across those two. And then what happens is it actually kills the microorganisms in a solution. So you can take a bucket of microorganisms in this bucket, and you stick this in there and you apply a voltage, and it kills the microorganisms. And so what happens is you start applying a voltage and the microorganisms will die. So this is the percent inhibition. And you can get up to, in 4 hours, you can, at 2.5 volts, you can get complete inhibition, meaning that you killed everything in this bucket of water by putting it in there. Now what could this be used for? So it turns out that generally when you get a bacterial infection from drinking bad water in a country like the United States where we treat our water well, it's because you've put ice in there. It's the ice maker. The ice maker has a chilled water compartment, and then when it needs more ice, it takes water from that chilled water compartment and feeds it into the ice maker, and then that will freeze. Well, in that chilled water compartment, it's just full of bacteria, because bacteria just begin to grow in there, and if nothing kills them, they just have a great time. So if you go overseas, there you're probably careful about drinking the water. But in the US, you're not careful about drinking water, but you can actually pick it up from the ice. And they learned this in hospitals, that people were getting these bacterial infections from drinking the ice water. So it actually comes from the ice. And so what you can do is you can take, it's a little pen-sized thing, and put a battery in there, and you can just drop it, and it floats in that little chilled water thing. So you don't have to retrofit. You can just drop this in, and it's applying a voltage, and it's killing all the bacteria. And when the battery runs out, you just put in a new battery and drop it in, and it'll float. It's applying a mild voltage periodically, and it will kill the bacteria in there. So you see that it could have tremendous applications. And then we made devices out of this. And so you make this interdigitated device, and so you see you have the graphene film here, the graphene film here, and you can make this into a microsupercapacitor. Supercapacitor is like a battery, but it charges really quickly. So it doesn't have the energy of a battery, but it charges much more quickly, these capacitors. And so you can build these little things. So look at our performance. We had about 15 milliamps per square centimeter. Just remember that number. 15 milliamps per square centimeter was what we first got. And then we could string these together in series. We can make two of them, string them together in series. So here's one device, and here's two devices in series. Or you could string them together in parallel, and you can get one device and then two devices in parallel. And then you can hook them up to an LED light, and you can use these microsupercapacitors to light an LED light. And then we wanted to show that this can be flexible electronics, so you can take the plastic platform, and you can flex it. And so it's flexible electronics. Most electronics that you have, you're not bending them. You know, they're very stiff. But here you can bend it. And you say, well, why would you want bendable electronics? It's like, why wouldn't you want bendable electronics? You can wear it on your clothes. You don't have to worry breaking. I mean, you can take your computer and fold it up, and fold up your cell phone and you know, jam it in someplace. And so here you can bring it through 6,000 bending cycles, and the performance is remaining the same. You say, well, how did you bend this 6,000 times? Like that. Graduate student, and he just bend it 6,000 times, and he'd bend it a few hundred times, record, bend it a few hundred times, record, and that's how you bend it. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. And so then we stack them up, and so you can make LIG on both sides. So you can see here the polyimide, and then you make LIG on both sides. And so now you can stack them up, you put an electrolyte in between, and so now you have stacked supercapacitors. And you can hook them up in series, or you can hook them up in parallel. And so you see they're going through all of these bending cycles. There's 4,500 bending cycles, and the behavior is remaining the same. Here's 6,000 bending cycles, and the behavior is remaining the same. So even in these stacked configurations, you can make flexible electronics. And there's no clean room. You don't have to go in a clean room and do all these crazy things. Just right there on your laser, you just print these things out, stack them up, and you got electronics. That's a big deal. And then you can deposit, we can deposit this manganese dioxide or polyaniline on the surface, and then what you get is you get this electrolyte in there, and it'll really increase your activity. And so then what happens is, this is called a Ragone plot, and this is looking at energy, and this is looking at power. So these thin film batteries, lithium batteries, will have a very high energy, but very low power. Capacitors have very high power, but very low energy, meaning that they dissipate a lot, but just for a short amount of time. Batteries last a long time, but they don't put out that much. And that's why, like in electric vehicles, what they've thought about is they'll use capacitors to really deliver a lot quickly in the acceleration, and then the battery takes over. Here you can get these microsupercapacitors, and here's a commercial supercapacitor, here's another commercial supercapacitor, and here's where we were with our systems, where you get these what are called now pseudocapacitors, where they sit somewhere between a capacitor and a battery. And again, this is with no lithography, no going into a clean room. So you can see the evolution of where we came from. Our first devices were giving about this 4 millifarad per centimeter squared. And then over time, as we got better at these, and then we go to the pseudocapacitors, we got up to 930, and now, then eventually we got up over a farad per centimeter squared. So you can see that this is in area, how we've improved. Here it is in volume, how we've improved. So you can see like this 10-fold improvement in volume, and this 250-fold improvement in area, in what you're able to do to build these devices. So these things happen as you go along. All right, what about an antenna? This was a pattern that a company had sent to us, and they said they wanted a 5G antenna. This is back when 4G was the thing. And they wanted this 5G antenna, and this is a 5G antenna written on a sheet of polyimide plastic. So think about the housing of your cell phone is made out of plastic, and if you could write on the inside of the housing of the cell phone your antenna pattern. That's what we're talking about. So when you can now write a pattern on a piece of plastic turns out to be a very big deal. You're writing out electric patterns, and you know, this is all drawn in a computer. You know, they send you the outline of what you just draw the computer, and these are the contact pads onto which you would bond wires. And then this was our mind-confined conception on how you could do this industrially. So you could take a sheet of polyimide, and it's rolled up, and then it would unspool. It would come in, and instead of having like you have on this laser system that I showed you, where you put down your sheet and the laser goes back and forth and writes this pattern, here you would have two fixed lasers, one for the top, one for the bottom, and as this rolls by, the patterns are getting written on there. And so you can use a lens to do this patterning as it goes by, and then it comes in, and if you wanted to deposit other things on the surface, you could go through electrodeposition, and then you dry it and roll it back up. That's sort of the simple industrial view of how you would be able to make roll-to-roll electronics. The whole idea was to be able, instead of taking silicon wafers and building electronics wafer by wafer, that you would just do it like you do newsprint. You know, you'd have a roll, goes out, it prints, and then rolls back up. And that's how you would do this. And so we'd found that you could modify the surface, you could put nanoparticles on the surface. So in other words, you could take these films that have of the polymer, you could make the polymer, and in that polymer you've deposited metal, and now when the laser goes by, you just deposit metal salts. When the laser goes by, it will reduce those metal salts to metal zero and deposit them as nanoparticles in those films. So you could put iron, molybdenum, cobalt in these films, and so you can see these nanoparticles in the film. And then you can do, this is an oxygen reduction reaction, so you can do electrochemistry based on these systems. And so you say, well, how could you make bulk catalysts like this? Well, what you could do is you could take a solid piece of polyimide, so you could make this polyimide that has the metal salts in it and make it into a solid log, you know, like a solid cylinder. And then what you do is you just shine the laser light onto this, and you take a cylindrical lens so it spreads the beam over this whole log. So one laser, you spread the beam over the whole log, and the log is going around. It's sort of like a gyro. You ever have a gyro for lunch or something, right? And so it's going around like this, and they cut it off, and then you eat this gyro. And that's why we call this the Giro method, because it gets cooked right here, and then as it rolls around, you have a knife blade that's slicing this off, and so you can make catalysts that way. So this is what I'm talking about. We are chemists. We're not automation engineers. But you just come up with a concept, and then automation engineers can take it from there and make one of these things happen. And that's the idea. So we build very simple little things, and then let the automation folks take it from there. Then we learned you didn't have to have polyimide. You could do it on any polymer surface. Anything that's made out of carbon, you could do it. But it turned out we didn't find that right away. We found it later on, and it turns out you have to unfocus the laser. If the laser is not focused, then you can start getting graphene. We would just get carbonized surfaces if we weren't using polyimide. It just happened to be that with a focused laser, polyimide forms graphene beautifully. But other types of polymers weren't working. But then we determined they could work. So how does that work? Well, for example, you could take, for example, cellulose. This is cellulose. This is what paper is made out of. This is what wood is made out of. All right? And it's just these glucoses stuck together, and then you have some other things on here. And then you put this in remember that little sealed container, and you put this in that sealed container, and then you shine the laser light, and you can write a pattern on wood. So this is now electronic pattern on wood. Well, why would you want an electronic pattern on wood? Well, now you have disposable electronics. I mean, it's just on a piece of wood. It's just carbon on a piece of wood. We had to do it in this box because the wood would catch fire if we didn't do it. But then we learned, as we did with the paper, that if you can just do it with flame retardant wood, it works great. So you just go to the hardware store, you say, I want to buy flame retardant wood, and then it doesn't ignite. So then you can do it in the air. All right, so what's happening here? So what happens is if you have a defocused spot, so if you just have this laser spot on polyimide, it will convert the polyimide into graphene. But if you have another polymer surface, it doesn't make it into graphene. It just makes it into carbon, it just carbonizes it, but you don't get all this nice six-membered rings. But what happens is if you defocus it, then you start getting graphene. So either you can use a focused laser and write 3 times. So first time you write, it carbonizes it. Second time you write, it starts converting that carbon into graphene. The third time, it completes it. And now you've got graphene on the surface. Or you can just defocus the laser. Because if you defocus the laser light, then you get, as it goes along, it's drawing these spots and it's overlapping the spots. So if you look at any one of these areas in here, they've all been written to at least 3 times. You see what I mean? So now you've taken the spot size, because what lasers do is they fire, fire, fire. So instead of doing that, so you defocus it so they start overlapping the spots. And as they overlap the spots, it's been lased multiple times as that laser went by. But it only had to write the pattern once, because on the next write, it was overlapping with the former line, and was overlapping with the former line again. And so just by defocusing the laser, so you can see here that if you defocus, it's the equivalent number of lasers. So you could do the equivalent number of lasers is if you defocus by about 1.2 millimeters. So you just pull it out of the focal plane by 1.2 millimeters. And that opened up now any carbon surface. This is all carbon. These tables are all carbon. The carpet's made out of carbon. If it's not glass or metal, it's carbon. We're made out of carbon. So here it is on a piece of paper. And again, we flame retarded the paper by dipping it in boric acid, or we sprayed it. I don't remember which one we did. Either can work. Cork. So cork is these carbohydrate strands filled with lignin. Or a piece of bread. Again, it's not dropping graphene onto the bread. It's converting those carbohydrate strands into graphene. See how important that could be? It'd be really important. And so you could write on a potato something. And here's a supercapacitor on a coconut. Here's a coconut. And here's a piece of cardboard. And so what you could think of doing is you could think of marking food, for example. So did you ever wonder, when I'm eating this potato, where did this potato come from? Is it from Idaho? Or is it from Texas? Or is it from like some very far place away that they spent a lot of energy to get it to my table? And so you can mark it. You say, well, that would just take too long to write a pattern on every potato. But if you look on your plastic bottles, you'll see there's a little numbers written on it with a laser. Every one of those plastic bottles is marked with a laser, and it's inscribed. So as these plastic bottles are going by, lasers are marking this so that they know where it came from. If, for example, it turns out to be something bad in that bottle and people start drinking it and dying, they can look, okay, where was that manufactured, and do a recall on that. So they're already writing on so many items. Now you can write directly a carbon pattern, and it's just like a charring of the surface. So it's really quite amazing. You say, well, then you might eat graphene. But you know, it turns out it's not bad, and it's not going to hurt you. And I know there's all these things that people say that there was graphene in the vaccines and everything. I don't know how you could have done that. There was no GMP source of graphene. And they'll show me patents. I said, well, lots of people have patents on things that were never used. So anyway, here I wanted to see if people were consuming graphene. And I'm not sure if I told you this, that it's in whiskey. Did I tell you graphene's in whiskey? So you know, if you drink whiskey, that has come out of a charred barrel. The barrel has been charred. And so I knew there had to have been some graphene in there. And sure enough, so I sent a student out to the liquor store, got a bottle of whiskey, we ran TEM, and you can see small amounts of graphene in whiskey. So people have been drinking this stuff. And so it seems not to be too bad. All right, and then what we wanted to do is we wanted to do 3D printing of graphene. So the idea is, could we take a polyimide sheet, take another polyimide sheet and draw graphene on that, and stick the two together just with a drop of ethylene glycol. Ethylene glycol is antifreeze for your car. And just the wetting forces would pull these two together and stick them together, and then lays on the top, and that would convert the rest of the polyimide into graphene. And so this letter R has been built from the bottom up. Layer by layer, it's been built up that way. And the other thing is, in the laser system, so that's the 10.6 micron laser. It turns out the 1.06 micron laser, which is also in many commercial systems, that cuts away graphene. So we made this little 1 centimeter by 1 centimeter block where we cut holes in it with the other laser. So you can make 3D patterns and then cut holes. This is just, can you imagine like going to graduate school and getting a PhD just to mess around all day? I mean, that's kind of like what this is. It's just really exciting. And then this was built by an undergraduate. And she built this, and she was really amazing. She built it in her dorm room. I mean, she got pieces of plastic. I mean, a lot of these pieces of plastic she made by 3D printing in the Oshman Engineering Design Kitchen. And then this is all 2x4 here, stacks of 2x4. And these motors I think she got from Amazon. And so then this is the laser in that same laser system. You can lower down the table, and this is writing on it. So you can see here. So there's so it's going by, and it's got the polyimide sheet is rolling out. Then this will write this pattern. And so this is in the laser box with the table lowered down. And you can see that how you can write these stacked patterns this way to build it up layer by layer. And then one guy said that he'd make a little pulse sensor. Again, this is really simple compared to what other people have now done. But these were the first ones, because we found this technique, so we were the first ones to make these devices. But you could just draw a line on this plastic, and then you put it around, and it's on your wrist, and you can even see the dichroic notch, where the pulsing of the heart. You know, you can see that, even that dichroic notch there as it's pulsing. And this is kind of what the Apple Watches I guess are doing now. This was before Apple Watches could do this. And then we worked with Dr. Miller, who's now left the university to start his own company in 3D printing of human organs, or organ replacements. But we worked with him to build this really nice system, and we built a nicer 3D printing system. Again, making laser-induced graphene. And so you could make 3D printed owls out of graphene. So this is a graphene owl, 3D printed. You can you can make an LIG film on one side and LIG film on the other. You put a little pinhole here to get equilibration in it, and we could deposit cobalt phosphide on one side, nickel iron on the other side. And so what you can do is you put a voltage across this, and you put it between two columns of water in these tubes of water. And then what you do is you apply a voltage, and it starts splitting the water. So you get water, from water you get H2 and O2. So you get you split water into hydrogen, and you split water into oxygen. And so you can see here the oxygen bubbles piling up. Now, let me just tell you, this water splitting to make oxygen, it's really amazing, and electrochemistry can be highly efficient. Its production rate is really slow, really slow. So that's the problem with electrochemistry, and until the world can solve that, all these electrochemical ideas, it just takes forever to make a lot of material using standard electrochemistry. And then we thought, you know, if you make a polyimide surface, if you come and just rub that surface, a lot of that graphene will come off. You know, so it's not real stable. And you do what's called a Scotch tape test. This is a formal test, Scotch tape test, and you write it in your papers. Everybody knows what it is. You take a piece of Scotch tape, you stick it to the surface of your material, and if you pull up, and now a lot of that graphene is coming off on the Scotch tape. That means it did not pass the Scotch tape test. Scotch tape test is just a very simple test to see how well something adheres. And so the idea was, well, could we stabilize this on a surface? And again, I didn't think of this. This is just the students thought of this, and so you get this. You get them thinking of these things, and so there's two different methods. So you make the LIG, you put a little mold around it, and then you fill it up with a filler. And so now you get a big polymer poured on it. So now you take it and you flip it over and you pull that polyimide off. So it's come off the polyimide sheet, and then now it's into that filler. So you've transferred the pattern. Now it's very strong because this filler is all around it. You see what I mean? So you could either do it that way, or you could take your polyimide that has the LIG, you put it on top of another piece of plastic, and then you put that in a hot press. So you heat it up and you push down on it, so then this LIG transfers into that sheet of plastic. So again, it's trying to stabilize a material. There is huge money in this sort of thing, making composite materials. And this is where the students took this and they used this commercial polymer called EcoFlex. So they made this pattern in LIG, and then they poured the EcoFlex in here. They pulled off the polyimide. So now you have this in an EcoFlex sheet. So this is this really stretchy polymer, this EcoFlex. And so now you have these patterns in EcoFlex. And so what happens is this is a LIG composite strain sensor. So this strain sensor has a gauge value of 1,000. That means that you can take a line of LIG, laser-induced graphene, in there, and you measure you can measure the current that goes through this, all right? Or you measure the resistance of this wire, of this thing, and now you stretch it. You stretch it 1/1000th longer, so just a very little bit longer. 1/1000th longer will change the resistance by 2 to 4 times. Well, why do you care about something that stretches a little bit? Well, if you have a bridge, you don't like that bridge stretching. So you have to measure very small increments in stretching. If you have a ship hull, you don't like that ship hull stretching very much because you don't want it to eventually break. If you have the frame of an aircraft, you don't want that stretching very much. So how do you measure stretching of a bridge? It's a very difficult thing because these stretch very little each year. And so here, if you have something with a high gauge value, if it stretches 1/1000th longer, you can measure. You can measure that just by measuring the resistance through that wire. So what you do is you find something. So you find this hammer, laser-induced graphene, and you look everywhere for a nail. You know, give me a nail to hit. Give me something to solve with this. So you have this hammer, and so everything starts looking like a nail. And you try to find something to apply to this. You guys will do this in life. You'll find something, and you say, how can I apply this to an area? And so this was something that the students made, again, very early on.
See?
And so
Because, yeah, you see, because of the...
you can hear them speaking in the background. So as they bend, the light starts flashing differently with the extent that they bend. So you can start building something that has sensors in that would detect motion. Now, years later, people came out with gloves that could read sign language. So somebody's doing sign language, and it could read that. So if you don't speak sign language, you could just read the output of that person doing sign language because it could read all the deformations in their hand based on LIG. So this was the simple thing that we did in our lab, where you just take LIG films and you tape it to a rubber glove, and then you bend the rubber glove. And then people took this and extrapolated it. You do something very simple and you put it out there, and then other people find good ways to do this. You want this internet model where you file patents on this, and now other people explore the space and start using it. But guess what happens if they use it? They have to license, sub-license from your patent. They have to get rights to be able to do this. So you've got them boxed in. So they find this really great application and you box them in. There was another group that made a voice sensor. So it's a little rubber thing that you stick on your throat. And as a person would speak, it could start to write just by the changes in inflection into the electronic signal in that little polyimide sheet. So you see the applications that could come from this. This was our tactile sensor. So, you know, again, this is these little strain sensors, these little sensors in a EcoFlex. And so this is a tactile sensor. So it's not even touching it. You just bring your finger up to it and you start building up this capacitance, and it can sense that you're getting close, and it gives this electronic signal. You breathe on it. You know, even if you breathe on it, it will detect you. And so you see that just the breath, it can detect it. And liquid sensors and breath sensors. So here's the response. This is one of these lines expanded. So this is looking at the current and picoamp changes. This was a composite Joule heater where you could take a glove and you could put this in there and you could heat it. So, you know, say you hurt your hand or something and you wanted a heater in there, or it's cold out. You can build a heater this way. And these could get blazing hot if you wanted it to. We'll see that in a minute. And then triboelectric nanogenerators. Triboelectric nanogenerators are things that when you bend or you flex them, they start generating this capacitance and you can start building up charge. And so the idea was, could we do that where we could have this polyimide and an LIG sheet and aluminum, and if you press these two together, you'll get charge to exchange. So this will become plus charge, this will become minus, and then you release it, and now you're going to get a current to run through this, and it will light up a light bulb. So pressing it doesn't do it. It's when you release, the current runs through. And then what you do is then the light goes out, you release, and then you press it again, and you can go on around. So every time you press this, you can start lighting up light bulbs with it. And so you can also do it this way. You could take LIG transferred to the PDMS and just put your hand next to it. You'll start building up a charge. So you get plus up here, minus here, and that should light up a light bulb. So when your hand lifts, you'll get this plus charge here. Now the minus charge is going to accumulate here, and a current will start running. So you see he has to start building up charge, and that's a string of LED lights that are lighting based on his hitting this little sheet. And so I said, walk around campus, start charging. So he left the lab, walked around campus, 1.2 miles, put that little sheet in there, and he started charging up this little capacitor. So you could think about, when I'm walking, I'm charging my cell phone, something like that. Wouldn't that be nice? You don't walk, you run out of cell phone battery. So. And they've thought a lot about this in the military. There's walking, and then also your arms are swinging. So you can generate from here too. So you have heel strikes, you have arm swinging, and so you start building up. It's just that you don't generate a lot by this, but as you get better materials development would allow you to get more and more from this, because think of how much energy is just wasted when you're walking around. If your heels are going up and down anyway, you might as well capitalize on that and generate something from that. You know, you can see that how they've done that in cars. When you're braking, it's charging your battery. Here, when we're walking, we're charging things as we're walking. These are responses to gases, and so you get gas sensors this way, and you can see that you get sensitivity to different gases. You can build this into cement and get these different gas sensors this way. And this was remember I told you about this student, John Lee, that was this amazing undergraduate here. And he did this. He took an iPhone and he put it on top of the laser. He bought like this $30 microphone on Amazon, because he had noticed as he was lasing the surface, you'd get different sounds. It turns out from the sound, you can get information on the quality of the graphene that's there. And so he put it through the fast Fourier transform, and you could tell whether you're getting good LIG or whether you're just getting disordered carbon just by the sound. So even as you're making it, just by the sound, you could tell. And then the last thing is he built this thing where you could bring gas through this, and you could pick up bacteria, you could pick up other things, and you could kill it. So as bacteria would flow through this, then you give an occasional voltage pulse, heats it up to 300 degrees, and kills all the bacteria. We published this in the fall of 2019. What happened in the winter of 2020? Nobody cared about bacteria. They all wanted to destroy viruses all of a sudden. And this could kill bacteria are much harder to kill than viruses. So we came up with this, and then here's the commercial product that came out of this. This is called a viral wall. So it sits on a little shelf like this. So you guys, you're always looking at your smartphone here, right? And you put this little device between you, and it's sucking as you inhale and as you exhale, it goes in here, and fresh air is coming out the top. As it's going through there, all the contaminated air, any viruses that you're breathing out, go through this, they stick to the graphene, gives an occasional voltage pulse, fries everything. And so you have like a virtual shield of graphene. I don't know if you can see it here, this virtual shield of graphene between the two people. It's sort of a virtual shield, because that's how it works, okay? So that's it. Are there any questions? If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.